Hello. We're at the final step for rendering our hello triangle. We've cut some corners, but it was still a long path. Well, it's time to climb the rest of the summit. I'll start by going to the header and adding two new methods, one called beginFrame and one called endFrame. These functions will do the administrative work, where we synchronize the rendering. So in the CPP file, we add the body of the begin frame and we duplicate it for the end frame. Now let's return to the main file and call these functions. In the loop here, we need to call begin frame each time we loop. And I realized that I didn't make those methods public. So let's go to the header file and make the begin frame, end frame, and render triangle public. I do this by copying them up here. Now we can call the begin and end frame methods in the main loop. Having done that, we can now implement begin frame. The first thing we want to do is wait for the previous rendering to finish up. We do this by calling wait for fences. We're waiting for one fence, which is the still rendering fence that we added in the last lesson. We set the vk true for the parameter called waitAll, and we set a timeout of the maximum unsigned int, actually unsigned long. This call synchronizes the CPU and the GPU. What this means is that the CPU will not continue until the GPU signals the fence by setting it to an active state. So since our fence is now in a signaled state, we need to reset it for the next rendering cycle. So we call vk reset fences to do this. This code will actually break here. In the first frame ever, we will not have a previous frame to wait for, and this fence will actually start up as not signaled. And if there is no previous frame, it will never be signaled. To correct this, we want to go to the create signals method. Here, where we created this fence, we can set an additional field for the flags. And we will set a flag to create the fence being signaled initially. This way, on the first frame, we can pass through the first wait for fences. Next, we need to pick an image to render. We can initialize the variable to 0, but to take an available image, we'll use vk acquire next image khr. Then we pass the logical device, the swap chain, a timeout to wait for, which I set to the max possible value again. Then we can have either a semaphore or a fence that will be signaled. We will not need to synchronize this availability with the CPU. So we just pass the image available signal for the semaphore and no handle for the fence. And finally, we pass in the address to an integer for the index of the image that will be allocated. This call is asynchronous in the sense that the image will not be available immediately, but we will get the index of which image will be prepared for us. Now we can call the begin command with the current image index. And I've previously forgotten that when we begin the commands, we also need to call vk reset command buffer to clear the previous commands and write new ones. Now at the end of the frame, we will end the commands, and then we will need to submit our commands for actual execution. So we create new submit info object and set the S type of that object. When we have the submit info, we need to tell the submit to wait for the image to be available. The image will be needed at a certain stage of the rendering process. This stage is called top of pipe bit, which is the beginning of the graphics pipeline. We set the submit info that the submit needs to wait for one semaphore. We pass in the image available signals address as the semaphore, and the stage mask is the address of the wait stage. We're going to submit a single command buffer, and we pass in the address of the command buffer. Next, we need to submit the trigger another semaphore when ready. So we set the signal semaphore count to 1, and we pass in the address of the rendered finished signal. Having this, we can now call vk_queue_submit. Here is where those queue objects come in play. Remember when we created the logical device, we also requested some queues. And I told you that we will submit the command buffers to those queues. We pass in the graphics queue, one for the count of submit infos, the address to the submit info, and finally the still rendering fence that we used in the beginning to synchronize with the GPU. We can check the success of this last call. And for rendering, we're going to throw an exception. Now, you might have connected that the image available signal is going to be signaled by the call to get the next image, and is going to be waited by the GPU before rendering starts. And submitting the frame for actual rendering is going to signal the fence, which we wait for being completed at the beginning of each frame. Then, what is this render finished signal's purpose? That will be signaled at the end of rendering. Well, rendering is a two-step process, and we had two queues. We passed the frame through the graphics pipeline, and we also want to request that same frame to be sent to the monitor. This is called presenting the frame. So we create a new present info object. Set the S type. We set that there is one wait semaphore, and this wait semaphore is the rendered finished signal. We set the swap chain count to 1. Then we set the swap chains to the current swap chain. You might have multiple swap chains in a case where you have multiple windows, for example. We also need to set the frames that we want to present to each swap chain. And here I actually want to make the current image index to be a member field. So I go to the header file and I scroll to the bottom. I then create a new index variable for the current image index. I can then start replacing it. Here at the begin frame I can delete the local variable, then set the field address here. And we can skip passing it as an argument to the begin commands. In the begin commands we can use the member field. And we also need to correct the signature for this method in the header file. Now, back at the end frame, we can pass the address to the image indices field. And we can call the vk_present_khr function. We pass it the present queue and address of the present info object. Remember that the graphics queue and the present queue can be the same queue, but it can also be separate queues. We also now have all synchronization covered. Semaphores, unlike fences, don't need to be reset since they are controlled by the GPU. Now, I build the project and I run the application. And here I have an error upon execution. So I break into the debugger to find out what I have done wrong. I follow up the stack trace and the error seems to be located here where we index the frame buffer. This means that our frame buffer vector is empty. Let's scroll down to the initialize Vulkan method. I quickly inspect this and we seem to call the create frame buffers, but the buffers are created from the image views. And I've forgotten to add the create image views method. Now the build passes again, and I'm starting the app. Well, we have another issue. It is still connected with the frame buffers from what I see. Now that we are creating the image views, there seems to be an issue in creating the frame buffers from those image views. So let's go see if the image views are created correctly. Inspecting the code carefully here where we move the iterator to the next value, I do not actually set the iterator to the next. Well, Everyone makes some mistakes, and this is way too much code to get on the first try. But this is the design of Vulkan. I build again, and finally we have no crashes. We start seeing the black frame. This means that we are successfully clearing the frame and passing it on the surface. We're no longer crashing, and we now have a black frame. The black frame indicates that the frame is cleared and displayed. Closing the window though produces an error. Now that we start rendering, the rendering is executed asynchronously, and destroying all the graphics object in the structure cannot just happen. We need to add a code to a function named vk device wait idle. We pass it the logical device. This means that we will wait for all submitted frames to finish before starting to destroy stuff. Now I do a quick build and run to check if all errors are gone. And it is the time for the grand finale. We go to the main loop, and between those begin and end frames we call the render triangle method. And building and running the project now gives us this nice pink triangle. It has been a long way, but we finally finished the hello world for graphics programming. Stay for the next lesson though, since we're going to advance even more with this knowledge.